In this video, we're going to look at calculations involving electromagnetic radiation. And the problem we'll work on is analogous to post-lab question number 4 in the hydrogen spectrum lab. In that question, you're given a table with multiple types of radiation, and for each line in the table, you're given one piece of information, and you'll need to calculate the information that goes in all the other columns. So what we'll need is a set of equations that links wavelength, frequency, and energy of a photon. And then to get energy of a mole of photons, you would simply multiply the energy of the photon times Avogadro's constant. So let's look first at our equations. Here's the three equations for electromagnetic radiation. The first is speed of light c equals lambda, the wavelength, times nu, the frequency. The second equation is the energy of a photon equals Planck's constant, h, times nu, the frequency. And the last equation is simply derived from the first two. The energy of the photon is Planck's constant, h, times speed of light, c, divided by wavelength, lambda. So let's work the first problem in the sequence, the ultraviolet radiation. I'm given a wavelength of 60 nanometers. The first calculation we'll do is to find the frequency. So we use this equation here. On the left side is speed of light, so let's plug that in. 2.9979 times 10 to the 8th meters per second, which comes from right there. That equals the wavelength, which I'm given, so I have that from my table, 60 nanometers. And then I notice that my units for wavelength, nanometers, is not the same as my units for speed of light. So I need to convert my nanometers for the wavelength into meters. For that, we'll use the definition of a nanometer here. Nano meaning 1 times 10 to the minus 9. Now I can make two possible conversion factors from that equality. I can put meters over nanometers, or the opposite, nanometers over meters. In this particular problem, I want to cancel nanometers and keep meters. So I'll put the meters side of the equation on top, 1 times 10 to the minus 9 meters, and on the bottom will be the nanometers. And we'll see that the nanometers here cancels the nanometers there. Notice too that meters on this side of the equation cancels meters on that side of the equation. So the only units I have left are the units of frequency that I want, seconds to the minus 1. Now it's just some algebra to solve for nu. I would take the left side of the equation, divide both sides by 60, divide both sides by 1 times 10 to the minus 9 meters, and I'll be left with the frequency nu. So I can really move to the calculator right now. Let's do that. So I have 2.9979 times 10 to the 8th. We'll divide by 60. And then we'll divide by 1 times 10 to the minus 9. Equals, convert to scientific notation, 4.9965 times 10 to the 15th. Let's plug that in. Now let's go back and figure out how many significant figures I can keep. If I look at my starting information, I have 3 sig figs here. In the speed of light, I have 5. This was a definition, so it's not going to contribute anything to significant figures. So my limitation is the 3 sig figs of my starting wavelength. So I need to cut off my final answer right here. The next digit to the right of that line is a 6, so I want to round up. So my final answer is 5.00 times 10 to the 15th seconds to the minus 1. Remember that trailing zeros right of the decimal are significant, so that number has 3 sig figs. Next, let's move to calculate the energy of the photon. So for that, I'll use this equation here. So energy of the photon is going to equal Planck's constant. I get that from right there. And that will be times the frequency that I just calculated, 5.00 times 10 to the 15th, seconds to the minus 1. Do a quick unit check. Seconds to the minus 1 here. We'll cancel seconds on the same side. So the units I'm left with will be joules, which is what I want. And now it's just a calculator operation. 6.62606,957 times 10 to the minus 34 times 5 times 10 to the 15th equals, in scientific notation, 3.13034785 times 10 to the minus 18. Let's plug that in. Now, once again, I need to round that. Too many digits. I see that Planck's constant contributes plenty of significant figures. So once again, I'm limited by the 3 sig figs of the frequency. I'll need to cut off after 3 sig figs right here. So my final answer will be 3.31 times 10 to the minus 18 joules. The last thing we're going to do is to calculate the energy in kilojoules of a mole of photons. So we'll start with the energy of 1 photon. The first thing we'll need to do is to convert that energy into kilojoules. So let's go back to our definition of kilo. Kilo is 1,000, so 1 kilojoule equals 1,000 joules. The conversion factor I want to make from that equation will have joules in the bottom, kilojoules on the top, so let's put that in. So I notice that joules down here cancels joules on the same side of the equation, leaving me with kilojoules. Next, I'll multiply by Avogadro's constant. Now, Avogadro's constant is here. Notice that the unit of Avogadro's constant is simply moles to the minus 1. So let's put that in. And if I look at the units that I have left, I have kilojoules, moles to the minus 1, which is exactly what I want in my answer up here. So now we'll go back to the calculator. So I have 3.31 times 10 to the minus 18, divide by 1,000, multiply by 6.022 times 10 to the 23rd equals, I get, in scientific notation, 1.993282 times 10 to the 3rd. Once again, I need to round to 3 significant figures here. So my final answer is 1.99 times 10 to the 3rd kilojoules per mole. Let's put all that up into our table. So there's our answers tabulated for the first problem. Okay, let's clear all of that and move to our next problem. What we're given for our infrared radiation is that the energy of the photon is 4.0 times 10 to the minus 20th joules. So the first thing I'm going to do is to calculate the frequency of that photon. For that, I'm going to use this equation. I have the energy of the photon on the left side, so I can put that in. And that will equal, on the right side, Planck's constant times the frequency. So there's Planck's constant. The frequency just simply comes from the equation. So now to solve for frequency, I would divide both sides by Planck's constant. So let's just turn to our calculator and do that. Move the calculator over here. We've got 4 times 10 to the minus 20th, divide by 6.62606,957 times 10 to the minus 34. Put that in scientific notation. So I find that my frequency is 6.0367612, and certainly many additional numbers times 10 to the 13. So go ahead and plug that in. Now let's go back and see how I need to round. So here's my starting information with 2 significant figures. My Planck's constant has many significant figures, so What's limiting is the 2 sig figs of my input. I'll need to cut off right here. When I do that, my final answer is 6.0 times 10 to the 13th seconds to the minus 1. And again, my trailing zero right of the decimal will be significant. Next, let's calculate the energy of the photon based on that frequency. I'll start with, I'm going to calculate the energy of the photon. Next, let's calculate the wavelength of that photon. So I'll use this equation. The left-hand side of that equation is the speed of light, so let's plug that in. And that's going to equal the wavelength times the frequency that I just calculated, 6.0 times 10 to the 13th seconds to the minus 1. To solve for lambda, I'll divide both sides by 6.0 times 10 to the minus 13, so I can go back to my calculator. So I have 2.9979 times 10 to the 8th, divide by 6 times 10 to the 13th, equals, in scientific notation, 4.9965 times 10 to the minus 6. Let's put that in. Now notice my units. Seconds to the minus 1 on this side will cancel seconds to the minus 1 on that side, leaving me with units of meters, which is what I have. Now rounding. Speed of light contributes 5 significant figures, so I have to go back to my 2 sig figs of my frequency as limiting. So I'll need to cut off this calculation here. I'll have to round up, so I get 5.0 times 10 to the minus 6 meters, corrected 2 significant figures for the wavelength. The last thing we're going to do is to go back to our original input, the photon energy, and we'll calculate the energy of a mole of photons in kilojoules. So let's start with our information, the photon energy. I need to convert that to kilojoules, so we'll go back to our definition of a kilo, 1,000 joules. I want to cancel joules and keep kilojoules, so joules will be on the bottom, kilojoules on the top. So joules here will cancel joules on the same side there. So then I multiply by Avogadro's constant. Once again, notice Avogadro's constant has units of moles to minus 1. So we'll plug that in. My units are kilojoules, moles to minus 1, which is what I want. So now we'll turn one last time to the calculator. I have 4 times 10 to the minus 20th divided by 1,000 and then multiplied by 6.022 times 10 to the 23rd equals 24.088 in units of kilojoules per mole. So let's put that in. Now, I'm not going to get any contribution of sig figs from the definition of kilo. Those are whole numbers. And this contributes 4 sig figs from Avogadro's constant. So my cutoff will be based on my starting info. I'll have to cut off right here. So my final answer is 24 kilojoules per mole. So let's go in then and put in all my information on the second line of the table. And there's my final result.